If you have been in a boat before, you will probably have experienced it rocking in the water, like this for example. The general motion of the boat is difficult to describe mathematically because it can bob up and down in the water, move horizontally, and rotate around various axes. Today we'll focus on a single element of the boat's motion, namely how it rotates from side to side around an axis parallel to the boat's length. This oscillatory motion is modeled by a function theta of t, where theta is the rotation angle of the boat away from its flat position and t is time. When the boat is sitting flat in the water, it is in an equilibrium position because it just sits there and does not rotate. For this boat, we know that this equilibrium is stable because if I push down on one side of the boat and then release it, the boat rotates back towards its flat equilibrium position and oscillates around it. We can use this timer to estimate the period of these oscillations. We can also use computer software to track the rotation angle of the boat over time to plot the function theta of t. Ready to count the number of oscillations? Go. 1, 2, 3, 4, 5, 6. Stop. We have observed that it took about 12.5 seconds for the boat to rock back and forth 6 times. Therefore, the period of the boat's oscillation is approximately 12.5 seconds divided by 6, which is just above 2 seconds. Based on our experiments, we have determined that this boat has a stable equilibrium, and we have a good estimate for the period of this boat's oscillations around that equilibrium. However, what if we wanted to design a new ship with a very different shape? We would need to ensure that this boat had a stable equilibrium, because if it had an unstable equilibrium, it would tip to one side when it entered the water and might capsize. This actually happened to a large Swedish warship called the Vasa in 1628. The Vasa was designed to be a tall and narrow ship, but the designers did not realize that it had an unstable equilibrium. Soon after it entered the water, it tipped over and sank. Once we have determined whether a boat has a stable equilibrium, we care about the period of the boat's oscillations around this equilibrium. This is important because if the oscillations are too fast, the boat will be uncomfortable for passengers or could damage cargo. What we need is a mathematical model that will yield a differential equation whose solution is theta of t. This will allow us to predict the stability and rotational motion of a boat of any shape, so that we can analyze the behavior of boats such as this one, or optimize the design of a new boat.